artificial intelligence. We objectively assess the importance of this topic. However, there is still no consensus on whether all tasks can be solved using these technologies. Abuse or obligatory use. We will raise such issues of ethics, modern information society, and cybernetics. This is the story of our virtual conference on pattern recognition and information processing in 2021, which has already begun. Here, right now.
And now we need to start immediately our session. But as Professor Dr. Kovalev, he had to present his results just in the first turn, but he need to come back to his laptop to open the presentation. I would kindly ask the second speaker, one of co-authors, Zhang, Shichao, sorry for my pronunciation of Chinese surnames, but the paper is whether recognition based on attention image search methods. I would kindly ask one of co-author now to have a floor and open the presentation. Is it possible? The second one, so it is 5.2. Yeah, I see here actually. So in our virtual platform, presenter, Mr. Zhang.
Here.
Pardon, lady.
Can you listen to me?
Unfortunately, I do not know actually. So now I understand. So, lady, please, could you start the presentation? So we will start from your turn.
Okay. I need to share my report.
Yes, we will wait, of course.
Okay.
Now we see your presentation. Please just make it a presentable way in a full screen.
Okay. Hi everyone, my name is Zhang. The title of my report is Weather Recognition Based on Attention Image Search Method. I will introduce our work from three aspects: background, method, and conclusion. Firstly, weather recognition is of greater significance for intelligent transportation, safe driving, and road monitoring. Especially, bad weather will not only greatly weaken the efficiency of transportation, but also cause traffic accidents, endangering people's lives and property. Recently, weather recognition method based on computer vision has become more and more popular. The traditional weather image recognition method uses histogram features and SVM classifier. Since 2014, the method based on convolution neural network has been applied to weather recognition, greatly improving the accuracy of weather identification. Up to now, most of the existing weather identification methods use a classifier to classify the weather. The model needs to be retrained when some classes are added or removed. In addition, the number of classes in existing datasets is insufficient, such cannot identify the conditions such as stagnant water or debris flow. The work of this paper mainly considers dataset, model, and generalization. For the dataset, we propose a final road weather dataset. For the model, we propose a weather attention module. It includes channel attention and spatial attention. For the generalization, we propose an attention image retrieval method to extract the image features, extracting features and compare them with the features of previous images to determine the wider class of the input image. In the train phase, combining the resonant network structure and the attention module as the encoder to learn the features. Then classification loss and metric loss can be employed to update the weight of the encoder. In the test phase, we adopt the encoder to extract features and compare them with the features of previous images to determine the wider class of input image. We draw the global average pooling map and a greater CAM++ map of common wider classes images, as shown in figure. The first row shows image in the ring class, and the model focuses the foreground and where the road reflects light. The second row shows the images in the snow class, for which the model focuses on the roadside position. In the third and fourth row, the model focuses on upper part of the road. The attention region includes the sky. This demonstrates that our model will pay attention to different information so as to distinguish different classes. Here we show the dataset comparison of proposed MTW dataset, as shown in Table 1, which contains 5 large classes and 11 small classes, a total of 2,444 images. The table below shows the generalization of the proposed model. The proposed MTW dataset is divided into different subsets: common cause classification, common find classification, and uncommon find classification. As shown in Table 4, in the first row, the CC subset, we can train the CC subset, and test on the whole dataset. We can get the accuracy is 93.1%. Experimental results show that the model can still get a considerable performance for classes that have never been trained. Then we conduct a series of experiments and analyze the effectiveness of our proposed method in Table 2. From Table 2, we can see that search recognition accuracy achieves 79.9%, which is improved 2.4% compared with the classification. From Table 3, the ResNet 50 achieved a better classification result than other ResNet networks. Our AIR method achieves the highest accuracy. This is our results. In summary, we propose a new multi-traffic weather dataset, and we propose a new weather recognition method based on the attention image retrieval method. Our future work will further explore the solution of some images containing multiple classes. That's all, thanks.
Thank you for your presentation. Please, now there is time for questions.
Okay.
No, we have none. I remind you that you may ask in also in Telegram chat, in our virtual platform chat, and also in YouTube stream. But I am seeing that we have none. Okay, so thank you again for your presentation. I guess you now streamed presented your paper just directly from Beijing. Yep. Okay.
Yeah.
Thank you for joining us. Well, the next presentation now from Vassili Kovalev, small image training sets, exploring the limits of conventional and CNN-based methods. The floor is yours, Professor, please.
Okay, thank you very much. I'm not sure right now I am succeed to sharing screen. Do you see my screen?
It is okay, just make it presentable way.
Okay, good. F5 or something. Bad. Okay, good. So my talk is about comparison of abilities of neural net based methods and the classical methods, and specifically the focus is on small training set, because you know that's a very important problem. So the motivation is there are always some rare cases, rare objects, seldom events, etc. And for instance, a disease in medical images. Some kind of disease come in every day in hospitals, but other maybe couple of only patient per year. So that's always exist. And there would be always situation of lack of computational power, because the large data sets always takes huge computational power, and sometimes it's available, sometimes it's not. And there will be always a reason to hurry up. We are living in real life, so we are often hurry up. And some other reasons. So that's the motivation why I'm focusing here in a small training set. So the image data I'm using. So I'm using 90 whole slide images of biopsy of 90 patients which are suspicious for breast cancer. And this is the subsample of images or whole slide images from chameleon challenge, which we took part. So image it looks like that, and maybe later on at the end I will show maybe more about that. But anyway, so here you see the tumor, which is large enough, and this magnification, and you see this. You see different kind of tissue. So this is tumor, and cells are different. This is still normal. So it's possible to sample images of norm and pathology from one single whole slide images. I suppose you already listened several talks and you understand that images are quite huge. So we can sample as much typically as we want, but they will be homogeneous, and that's another problem. So anyway, that's the example. So I created, for benchmarking purposes, of course, I created a data set which consists of 12,000 images of like that, 256 in size, and that's the examples of norm, and that's examples of tumor. Oh, let me switch. Yeah. Pointer. So you see that they are very homogeneous, the data set in homogeneous, they are very different, and that's make problems, but nevertheless it's possible to do classification. So I'm considering binary classification to make the things easy to understand. And then about data sets. So all the data sets, small and big, they are all perfectly balanced. That means no pieces of whole slide from one patient goes to training set and test set simultaneously. So we subdivide 70 to 30 data set for training and testing, and also the test set consists of 3,600 images, and that's training set used everywhere in all the experimentation and never changed. So about methods. So the classical methods consist of 3 steps mostly. So the original RGB color images using adaptive methods reduced to 32 colors. Histology images reasonably poor by color space, in terms of color space. Then the co-occurrence matrix is computed, like occurrence in space, the different colors, and that's very well-known technique. In particular, one of the paper I'm proud about is still people cite it. It was with Stefan Vollmer we have done in 1998. And then, of course, that features are huge and correlated. Then we are using the principal component analysis method to reduce with different thresholds. So it's resulted in 20 features, like what are principal components, 200, 400. So I use almost everywhere, essentially, this one, 200 features. And I use, for the beginning, I use very simple convolutional neural network. You see how many filters, etc., and then after flattening the fully connected network as usual. So that's very primitive. Why I use it? Just to make everything clear and clean. And then, afterwards, I also use 4 different commonly known different neural network architectures, which are listed here. I never understand whether this Zoom stuff visible or not. Anyway, the trainable parameters are shown here. So the first one is 23 millions and some different others. So the pipeline, we start from the pipeline of all experimentation is that we start with 8,400 images as training set, and gradually then reduce it by 10% down to 840. In addition, 840 will go further, and we deal with the training set of 400, 200, 100, and finally 1% of original data set. Of course, sampling is done randomly, and everything is perfectly balanced. So, and every experiment repeated 100 times. Because to get the estimate, the reliable estimate of classification accuracy, some other results. So here is the result of classical methods. Of course, at the end, we are using the classifier. In this particular case, this is support vector machine and random forest, which are very commonly used everywhere. And that's the size of training set. And once it goes, you see it goes, to 800, almost with the same accuracy. That's very small difference, actually 1%, something 1.5 maybe percent. And then it drops dramatically after 800. But in general, it is not zero accuracy. So you see 96% and 89%, not that much difference. So it's acceptable, actually. And that's the spread of accuracy in every experiment as a result of classification on different subsets, on different samples. So you see that at the beginning, the results are reliable. They are not depending on the actual content of training set. Then once it's getting smaller, the spread is really very high. So that means with a very small data set, like 84 images only, by chance you will get very high classification accuracy, and maybe you will get very low one. So it depends. We never know how to put which images to put to training set to cover the feature space perfectly. Otherwise, it would be possible to do. So that's the results. Final results, and you see SVM on co-occurrence features doing pretty well, and almost always outperform this neural network, which is something, by the way, not that small one. So it's you see 57,000 of parameters. And if we take a maximum of support vector machine in random forest, then that's the blue line. It's outperformed CNN, convolutional neural network, everywhere, you see. And that's another result of another experiment. So we tested 4 different architectures. They are shown here, and also repeat everything is 100 times. And we got for every data set, we repeat 100 times. So that 5 guys finally is 500 circles of training and prediction. So it's pretty computationally expensive, by the way. So we see that very funny results. So that's a mobile net version 3, NASNet mobile, and efficient net B2. They are in some way similar, but this new one, which has appeared very early, demonstrates very impressive behavior. So it's almost independent, result almost independent on the size of training set. That's amazing, actually, for me. And there's the result altogether, and you see, so that's the data set, training set size, as it was before that, the accuracy, and how it drops for different neural networks. And this is support vector machine, and you see it's almost the same result like the best classical, very heavy, with millions of trainable parameters neural network. So that's the end. The computing was done using this server, which is reasonably fast, reasonably powerful. It's equipped with 4 GPU graphic cards, NVIDIA V100 with reasonably high graphic memory on board. So, okay, conclusions. The first conclusion is that high in-class variability because of nature of images leads to a broad range of result on small data set. In our case, it ranges for the same things from 73 to 95% in this particular study. And the results produced by conventional methods are very comparable with the ones which produced using convolutional neural network, even with the heavy architecture. And this particular study, this network shows amazing the result, but traditional approach with co-occurrence matrix features and followed by SVM produce almost the same result. That's my conclusion. So that's it. I don't know whether I'm still in time or not.
Thank you for your presentation. You're right on time. So the
that's good.
Very clear. I hope we have questions.
So I invite everyone to our website, which is image.org.by. Image.org, like organization, org.by. And you will see a lot of things like that.
Is the idea already realized on that demo applications on the website? I mean,
yes. Yes, there are different kind of things on web. For instance, just in the context of my today's presentation, that's the whole slide images, and we are dealing with them. There is a specific tools to find out specific regions. That's a pretty good way to do automatically different kind of things. You see, that's navigation, that's ordinary things, but it's done in web technology. That's really bad things. And if we want to extract such bad things, we can do this automatically. You just select it and press the button, and it goes through this huge image, and finally it will produce heat map. Now you see heat map. That's the red things of heat map. It's pointed out to very bad. In our case, that's the cancer breast cancer, very bad regions, and then you can set up a threshold, and all that regions would be exported as a small tiles like that one. That's the result of searching automatically. So it's something like content-based image retrieval, but the retrieval do it by scanning this huge image. So then you just, in few clicks, you will get your data set. What is really efficient, I would say. Thank you.
Thank you. Dr. Vassili Kovalev, I would like to ask you, how about with that project about skin cancer by mobile phone cameras?
Oh, well, first of all, it was not, we were just participating in this project. So the major, well, that's long story. Anyway, the key person who was leading the project unfortunately died unexpectedly. So I'm not taking part in this project anymore. But in general, if you have a data set of labeled lesions, skin lesions, then it's just a matter of 1 month to do the system, and then to port it to mobile solution, to web solutions, etc., etc. So it's not
that way. Just client, yes. The computational is done on server.
Of course, it's impossible to do this heavy computation. So it goes to that powerful computer, which is you see that there are a lot of different things, like even that CT segmentation, lesion localization, searching for COVID lesions which affected the human person, and everything is done in the large computer, and you only have access. You have ability to upload your images and get your results. Also, one version, this version is working right here in our building on our servers, but another one working on the Amazon. So you need to go to TB, tuberculosis portals, and there are a lot of different sub-portals, and another version is working on the Amazon, and it's on the roof of National Institute of Health of the United States, NIH.
Okay. Just one more question from myself, from my side. What do you think? Is it possible to apply this CNN, which is small data sets, to other fields, at least for those for cancer and for skin, or probably for satellite images as well?
No, well, actually, it's dictated by the variability of images. So if they are homogeneous, like suppose you have a texture, homogeneous texture, how many pieces you have to represent the image, the whole image? Just one, because it's homogeneous, it's the same everywhere. And then, okay, imagine that just photo of street, etc. How many you need? Of course, there will be people, there will be some cars, there will be buildings, trees, blah, blah, blah. That's high variability. You need more, otherwise you will not succeed. So it depends on the variability of your images, and of course you will do different kind of things. So variability here in my benchmark is also high, but nevertheless it is capable. You have noticed, images came from different hospitals. Sometimes they do, for instance, colors very different, etc., etc.
Oh,
so it depends on several things.
I would kindly ask you to open the chat on the virtual platform and just repeat the question which was typed there, or speaker. I mean, our participant may do it orally.
Thank you for really interesting presentation. Thank you as well. If I understand right, is neural networks for your task not the best at all? Not. It is not. It is not, because they outperform in general case. So I was focusing on small data set and use it as benchmark. But really, because of this whole slide technology coming to real practice, you can obtain a lot of images actually, and but variability is very high actually for histology images. So if you are living in Minsk, you would be proud to know that our Minsk Oncology Hospital, Central One, is very well equipped with this recent technology. I mean, from Switzerland, they got very nice scanner, very expensive one, but very nice one. It's a 200,000. And also, by the way, this server, I'm thankful people from European Union who provide us 100,000 euro to buy that nice server. We are using this for teaching, for science, for research, etc., etc. We are very much thankful for that money. That's big money, actually. Thank you.
Many thanks. Yep, thank you. Yeah, so I would like to thank you again. So you are like a champion of our conference. Yes, having plenary talks, participating in panel, and now your own presentation. Thank you.
Okay.
And now I would like to invite the next speaker, who will present results entitled "Automation: The Study of Radiologically Isolated Syndrome and Multiple Sclerosis." So,
hello.
Yes, exactly. So, Ivan Kosik, yep.
Yes, Ivan Kosik. Can I share my screen? Do you see this?
Yes, it's clear now.
Okay, the volume is good.
Enough.
Hi, my name is Ivan Kosik. I'm a researcher of Belarusian State Medical University and a graduate student of Belarusian State University. Our group of researchers and scientists are working on important and interesting project, the main purpose of which is to help doctors to perform a quick and accurate diagnosis of a patient condition with multiple sclerosis. And today I want to present you some results of our work. First of all, I need to say a few words about the multiple sclerosis disease. It's a very serious illness of the central nervous system, which leads to disability. It should be especially noted that this disease leads to disability among young people of working age. In addition, pathogenesis of this illness is still insufficiently understood. There are a lot of factors which can contribute to its progression. And one more main fact is that frequency of disease occurrence is increasing. Therefore, we need to put more effort into multiple sclerosis studies. The most important diagnostic feature of multiple sclerosis is focal lesions of the central nervous system. MRI or magnetic resonance imaging is the most effective tool for lesion visualization. On the animated picture, we can see some slices of MRI image with multiple sclerosis lesions. They are selected by blue color. To make an accurate diagnosis, a doctor has to analyze parameters of all lesions. And to get accurate parameters, we need to perform precise segmentation. But segmentation of multiple sclerosis lesions is not a simple task because they have poor contrast and blurred boundaries. In addition, doctors have to spend a lot of time to process all MRI slices. One MRI contains about 30 or 40 slices in average, One more problem is to analyze multifocal patterns where number of lesions is very large. So manual segmentation is long and even boring process. And we want to solve this problem. And to do that, we propose to use segmentation automation using neural network. First of all, we need some training data. To get them, we collaborated with doctors from 9th City Clinical Hospital of Minsk. We got 445 3D series with different MRI modes and orientations from 50 patients. Ground truth masks were created using our application with semi-automatic segmentation using Smart Brush tool, which based on classic region clustering. You can see how it works on the animated picture. It's a classic algorithm. The modified UNet 3 Plus was used as a neural network architecture. Left part of it, so-called model encoder, was replaced by VGG16 backbone with ImageNet pre-trained weights. To train neural network, our 3D series were divided into two sets, training and validation, in the ratio of 75% to 25% accordingly. The plain slices with lesions were extracted to train two neural network models. First one using only series with 2T MRI mode, and the second one using all MRI series. To increase data variety and get better algorithm accuracy on new series, we have used data augmentation during training. The augmentation library was used to perform most of data transformations, such as rotations, shifts, scaling, reflection. A little more specific augmentations were used too, such as sharpening, gamma change, optical distortion, and our custom augmentation, which creates random side patterns. To evaluate network quality, was used intersection over union metric, which calculates the ratio of the intersection area to the union area of ground truth and prediction masks. Addition series of 15 patients were used as a test set. And the best obtained accuracy for the trained model was 0.62 intersection over union. It's for our model, which were trained on T2 MRI mode only. Train parameters for this model are presented on the slide. The main one is loss function, is combination of a binary cosentropy and dice loss. You can see here training time, it's about 4 hours, but for our other model, which were trained on all series, it was about 10 hours. Results of lesion segmentation using neural network are presented on the slide. Green color is ground truth lesion mask, which was selected by doctor. Red color is mask of network prediction, and the yellow color is intersection of both masks. Segmentation is done on slices with different MRI modes. On the left, you can see T2 flare mode, and on the right, T1 MRI mode. The second one, slide with segmentation results. So, neural network can process one slice of MRI in about 1 second. So, to process full MRI, it's about 30 or 40 slices. We need less than 1 minute. For semi-automatic segmentation, the same process can take 20 or 25 minutes in average. So good automatic segmentation accuracy and relatively fast full MRI processing allows to save doctors' time and efforts when working on patients with multiple sclerosis. Our next plans include testing of classification-guided module to train networks on slices without lesions. And second, we are going to test usage of several neighboring slices as model input to improve segmentation accuracy of lesions located next to brain sulci. That's all. Thank you.
Thank you for your presentation. So please, now we have time for questions.
Alexei, I'm sorry for appearing once more. I promise I will be disappearing soon. Okay. Anyway, I've got questions. I was expecting this phenomena, multiple sclerosis, is very well known for years and years and years. So there are many works, a lot of works on that, on segmentation of that kind of lesions. So, but in this work, you never compare, at least in your presentation, with the results which achieved by others people, which are reported broadly in literature.
Yes.
So it's like a tradition. If we are in Belarus, we are not. The world is Belarus, so we are never compare anything to anybody else. And also, I noticed something unusual a little bit on ventricles. So they label it as multiple sclerosis, but to me it appears as a periventricular hyperdensities, which are common, sometimes appearing. They are not cognitively affecting people, but nevertheless, it's on the upper part. So please, but this you should not comment, perhaps it doesn't matter right now, but what about comparison with the best results achieved in the world? There are so many of them.
Yes. Of course, there is a message which allows to segmentate lesions, and first of all, the classic ones, which uses such algorithms like region growing, that's all. They work very good, but they are semi-automatic. And for example, we use them to get our training data. You can see here, for example, it's a semi-automatic algorithm based on region clustering, and it works good, but you have to do this process on every slide, every slice, and it's not very fast process. There is algorithms which works fully automatic, but it works good on some images. But when you get another one, it work bad, and you have to edit these results. New methods which uses neural networks work better than classic one for such task because these lesions has a very poor contrast. We have analyzed one work which uses neural network for full 3D, and even not one 3D, it uses two 3D MRI modes to analyze lesions. First of all, not all our hospitals has devices to get to these MRI modes, and the second problem that it's very hard task for their devices. We cannot do that on weak computers of doctors, because neural network which uses very big data, like 3D volume, need a lot of memory, and it takes a lot of time. So we decided to use only one slice and train our neural network to work with 2D images.
So actually it's 2D, but nevertheless you haven't supplied, unfortunately, the references and numbers of works done by other people on this problem. The very short question appear that, okay, by definition, these kind of lesions are in white matter because this white matter demyelination problem. Biologically. So have you faced the cases when your neural network, when your software find false positive cases in gray matter?
Yes, the main problem, yes, of course, sometimes our algorithm will detect wrong segments, and so we allow the doctor to edit the results using classic methods, of course. And main problem it's here on the slide. It's to detect lesions which located next to brain sulci, because when we use only one slice, neural network cannot analyze its brain sulci or its lesion. When the doctor do it, he can just use next slice and previous one and analyze what is it, his lesion or its brain sulci. But when the neural network do it, it's impossible. So our next plan is to use three neighboring slices to resolve this problem. For example, we can put these three slices into RGB channels of one image. So our neural network will use not so much memory like other network which uses all 3D, and we can use it on weak computers, but the problem will be solved.
Yeah, that's a very common approach. Okay, thank you very much. Next time it's better to say not sulci but sulci. That's
okay.
Be more correct.
Thanks.
Okay, thank you very much
for the presentation and for your discussion, colleagues. Now we need to go to further to the next presentation. I hope it will be made by Oleg Naidanovich, Alexander Nedzved, or Shipin Yi. Please, who will present DSD-Net neural network for shadow detection from urban satellite images?
Yes. So, can you hear me?
Yes, clearly, and we also see your presentation. Just make it.
Okay, no problem. So this is my presentation. Good morning, dear colleagues and participants of PRIP conference. My name is Oleg Naidanovich, and I'm a third-year student of Belarusian State University in the Faculty of Applied Math and Computer Science. Today, I'd like to present you a scientific research, which is called DSD Neural Network for Shadow Detection from Urban Satellite Images. So the main purposes of this work are to present you a destruction-aware shadow detection neural network, retrain it on urban satellite images, and analyze the efficiency and consider their obtained results. So at first we have to determine why dealing with shadows on the image is a significant problem nowadays. So the presence of the shadow can degrade the performance of many fundamental computer vision tasks, such as semantic segmentation, object detection, and visual tracking. So the main the main problem caused by a shadow is a loss of information on the image, and it can lead to destruction of various parameters derived from pixels, so area cannot be interpreted correctly. Next question is why neural networks are used to solve such problems. There are many traditional approaches which are based on color chromaticity and elimination cues. However, in satellite images, there are often non-shadow regions that emerge like shadows, and there are detected shadows. Also, there are shadow regions that emerge like non-shadow patterns, and there are detected as non-shadows. So now it has become possible to use deep learning techniques to computer vision tasks. Such techniques are based on capturing contextual information and exploring context and internal simplicity of the image. So some words should be said about the approaches to solve the above-mentioned problem. Convolutional neural network, DSDNet, was used for shadow detection. In order to construct a multiscale neural network, it was used ResNet 101 as a backbone network, which is pre-trained on ImageNet dataset. It's also possible to use other different backbone networks, which with the same size of features. So these subnetworks allows us to create layering, as it consists of 5 layers. These backbone features run through each scale and get into DS models. So each of DS models will take image features as input and produce DS features, which catch the destruction semantic. And the DS model is used in order to learn semantic features of the destruction regions and concatenate them with the input image features to produce data, which are used for shadow segmentation. So in the end, the DS features are concatenated from top to down and finally sent to a fusion layer to get the final result. So the next step is metrics. So balancer rate was used as a metric to calculate the efficiency of this model. This metric is the average of errors on each class. Since we are trying to solve the problem with imbalanced data, we should use such metric which will be more resistant to imbalanced data, and BEER is extremely used for shadow evaluation. So the lower score of this metric represent the better performance of our model. The next step is datasets. There are 3 main datasets which were used in training a neural network. It is USV, SBU, and ISTD. In order to expand the training sample, all pictures were augmented by random horizontal flipping and were reduced to the size of 312. Finally, we have had 6,100 images on the training set and 1,300 images on the test set. As we solve the problem of supervised learning, there are labels for each photo which look like a binary map. Moreover, we have retrained our model on the sets, on our own sets with labeled urban satellite images. So this slide represents the results of the neural network. As you can see, it deals well with most of the images. However, there are many cases where the network gives inappropriate results. It can happen either on weak shadow images where the shadow have very similar brightness to the background. This problem can be solved by adding images with complex cases to the training set. On the basic of the obtained results, we can conclude that this neural network deals well with this problem. BEER metric gives high results, which prove that it's one of the best state-of-the-art approaches among deep learning models. Having analyzed the efficiency, the effectiveness of using this DNet, we come to the conclusion that the creation of new data sets will be a further development of this neural network to improve its efficiency in order to solve the issue of shadow segmentation from urban satellite images. That's all. Thank you very much for your attention. I'll answer any questions if you have them. Thank you.
So, any questions? I see none. The same in different channels we have. So, thank you for your presentation. Clear and quite pressed. Now we will move to the next presentation, next speaker. Alexander Usatov and Ivan Kosik identifying the presence of COVID-19 on X-ray medical images using a neural network.
Hello there, can you hear me?
Yes.
Right, now I'll share my screen. My name is Alexander Usatov, and I am a master student at the Faculty of Applied Mathematics and Computer Science of Belarusian State University. Also, I work as a data scientist at Platform.io and teach algorithms and data structures at my faculty. Today, the problem of COVID-19 in the world is, to say the least, urgent. Therefore, many researchers have paid their attention to pandemic-related topics. I could not stand aside, and that's why I want to talk about identifying the presence of COVID-19 on X-ray medical images using a neural network. This is two X-ray pictures. On this, you can see patient with coronavirus, and on this picture, a healthy one. The goal of work was to build a model capable of automatically identifying the presence of COVID-19 on X-ray medical images. One of the most common approaches to object recognition in images is convolution neural networks, which got chosen for our work. Convolution neural network use convolutions to get information about environment, neighborhood of a pixel in our case. You can see an example of a simple convolutional neural network architecture in this picture. Now let's talk about data set. We've used in this research, we use public open data set of X-ray and CT images of patients which are positive or suppressed of COVID-19 or viral and bacterial pneumonias. Data was collected from public sources as well as through indirect collection from hospital and physicians. All images and data will be released to publish on GitHub. There are about 1,000 images in dataset. On these pictures, you can see two examples. These examples of our used dataset. Now about neural network. We've tried to use a full convolution neural network for object detection as basic method. In view of the enchanting success of deep convolution neural network in 2012 ImageNet competition, the field of deep learning has experienced a huge increase in popularity, and significant number of different neural networks architectures have emerged. To avoid the vanishing gradient problem that sometimes occurs with the usage of popular ReLU activation function, the YELU activation function has been used instead. You can see ReLU graphics here and YELU graphics here. And on this slide, you can this slide shows the first architecture of using convolution neural network. So one of the possible and the most basic simplification of our model is to reduce the dimension of the input data by converting image to black and white instead of usual RGB input. It's important to understand that this decreases the amount of incoming data only for the first convolution layer. And since the number of output channels is specified by another parameters. Let's check the difference in training time for the network we used with the number of input channels equals to 1 and 3. With 3 input channels, the neural network has been training about 6 minutes. And with one, it has taken about 5 minutes 30 seconds. The training carried on the NVIDIA 1650 Ti GPU and increase in the number of input layers from 1 to 3. Training time, they increase the training time almost 7%, and does not give a noticeable increase in quality, which indicates that useful of the proposed approach. Now about quality metric and result. In diagnostic tasks, positive examples are more important than negative ones. Therefore, priority was given to positive examples. There are a little bit more positive examples in our dataset. The confusion matrix on the test dataset can be seen in the following table, and ROC curve look like this. Next pictures show an example of input image and a map of cumulative intensity of convolution layers after 19 layers for this image. After smoothing, the weighted sum of image shown in the here. Conclusion and further research. Segmentation is helpful in a small database. However, it has also been found that augmentation many images from a small set influence model accuracy because of the addition of noise during model training. On the other hand, a very small number of images does not produce the best result for any model due to underfitting problems in the pre-trained model. The promising result obtained using convolution neural network models suggests that chest X-ray can be useful for early detection coronavirus comparison to that time consuming pathological test or costly CT scan. It's possible to use more complex neural structure. There are two options: either think neural network from scratch or fine-tune some already existing model. For example, YOLO. Scientists show impressive results in other tasks. The variant with training a large neural network from scratch takes a lot of time and probably a significant increase in the training sample to prevent the neural network for memorizing the training sample and insufficient volume. To build a bridges map, you can use a weighted convolution value that will consider the weights in fully connected layers. This will allow to determine which areas are original images, take the greatest contribution to more accurate to the result. The question of need to use data augmentation remains open. There are reasons to there is not sense in this. The X-ray images are similar to each other. Science people are the same postures during the X-ray examination. Also, all images are usually taken from one and the same distance and angle. So, thank you for your attention.
Thank you for your presentation. So now we have time. Thank you that you were so clear and pressed, and we are right on schedule. So questions now?
I got one.
Okay, you may.
Okay. Well, to ask the question, I need to share the screen. Is it possible? Okay.
The question was asked.
That's my screen.
No.
Okay. Let me first show this one. First of all, I am very happy to see the student working on that domain. That's very encouraging because I'm a little bit playing the role of teachers. So I just want to inform you about the results which we got in the worldwide competition on that challenge on COVID detection. So that's the examples, and we are in top 10 in the world, and we are on the position number 6. And we are just not foreigners. We are here working here in Minsk, etc. So it would be nice to see you, to communicate, etc. That's point number 1. The point number 2. This is the screen. Do you understand? Do you see which image it is? So it's 99.9% pathology, because that. Okay, I just catch the screen of your presentation. I was going to catch both of them, the abnormal and normal, but you just moved and I was not succeed to catch it. So anyway, there is if you don't know both of that occasion, so there is that kind of things, and they are implemented already and available in software and tested in the international environment. And the second, there is another, this one, which is also available, also tested, etc., etc. So that would be good idea to communicate. Not very good idea to use that X-ray for COVID, but still it's possible to do with the CT, etc., etc. So it's just invitation for cooperation. That's it. Thank you very much.
Thank you for your comments. So, speaker, you may answer if you would like.
So I can write my email in chat and you can communicate.
Yeah. Good.
Okay, let's go to the last presentation of this session, which will be made by Mikhail Kharinov, super pixel clustering for detection of binary object hierarchy using modernized classical clustering methods. So, excuse me, could you stop sharing the screen? Yes. Mikhail Kharinov, you have a floor now.
I have some problems with connection, but I try to start the presentation.
Yes, we see your presentation now. Is it possible just to make it in full screen mode in presentable way? Yes.
So, do you hear me?
Yes, we can hear you and we can see.
My name is Mikhail Kharinov. I am a senior staff researcher of St. Petersburg Research Center of the Russian Academy of Science. My report, entitled as above, is devoted to the problem of object detection in any image, regardless of its content. So our talk aims to present a rigorous model for object detection in a digital image of arbitrary content. To build such a model, it seems useful to answer the following questions. First, what is the stumbling block of modern methods for object detection? Second, what does the image consist of? Third, how to describe objects without referring to the specific examples. And next, do the visually observed objects form a hierarchy? Next, is the image a hierarchical structure? Next, what is a sufficient system of methods for object detection? And last, what is the adequate data structure? After the model presentation, we will answer the listed questions. The model of object detection has been built up over 30 years by trial and errors. As the final model statement, the rigorous definition of superpixels through the intersection of optimal image approximations has recently been found. This definition is illustrated on the slide. Let the top row of picture show the optimal approximation. Then the bottom row of pictures shows the superpixel hierarchy. Note that the optimal image approximation by 4 clusters does not ensure the reproducing of no one of previous optimal image approximation due to the erasure of the sharp boundaries between the optimal pixel clusters. The slide illustrates the same definition of superpixel using a standard image, Linna. The slide shows the graphical characteristic of superpixels. Notice the difference between the solid curve and the dashed line on the left slide. This indicates that the sequence of the optimal image approximation is not hierarchical. The graph on the right shows that the superpixel hierarchy is not convex. Moreover, it's not binary. The slide shows the numerical characteristics of superpixels. Usually, in the considered range of cluster numbers, no one even tries to calculate optimal approximation due to excessive computational complexity. However, this is not at all the case that this slide demonstrates. The slide describes the target model of object detection. In our model, the problem of approximating of a non-hierarchical sequence of optimal image approximation is posed and solved by means of a convex binary hierarchy of suboptimal approximation. The latter contains an optimal approximation with a given number of pixels clusters. Due to the ambiguity of the solution to the optimization problem, two independent tuning parameters appear in the model, namely the number of superpixels and the number of basis objects in the image. To work with optimal image approximation, our model provides three advanced methods of classical cluster analysis. Namely, what recursive method for clustering pixels by image path. The second method, the reversible clustering improvement split and merge method. And the third method is the accurate Camillus method. It is Kamin's method improved by Sergei Dvoyenko. For active practical implementation of the model, it would be extremely useful to develop and strengthen the original method of cluster analysis, which are included in MATLAB. All calculations in the model are reversible and performed in terms of a special data structure. This data structure is the so-called algebraic multilayer network, AMN. AMN consists of dynamic Slater-Tarian trees and cyclic graphs, which are used for high-speed computations. Specific algorithms are fairly long story about routing computations. In summary, let's answer the questions listed above on the second slide. In the sense of our model explains the difficulty of object detection due to the disappearance of sharp boundaries between objects in the image. Our model represents an image as consisting of the minimum sets of the elementary superpixels that ensure the error-free construction of several initial optimal image approximations. Our model also describes objects in the image as unions of parts of a specified number of basis pixel clusters. Then, our model supports the detection of the hierarchy of objects in the image and treats an image as a superposition of object hierarchies, which is not a hierarchical structure. Our model provides a system of three modernist classical methods of pixel clustering to detect objects. And last, our model provides network reversible speed-up computation in terms of Slater-Tarian dynamic trees and cyclic graphs by means of the so-called algebraic multilayer network. Thank you for your attention.
Thank you for your presentation. So now if anybody would like to ask a question, you may. So I see none. So in this case, I would like to close this morning session. So, and we will continue at 12:45. So many thanks to speakers. Let's come back to
My connection is unstable.
Yeah, thank you. 12:45 and start the next session.